In this video, we will cover two problems from continuity. These problems are taken from the past finals. What I suggest you is that you pause this video right now, copy the problem, okay, and try to solve it by yourself first of all, and then compare your solutions to the solutions that I have that I'm about to present. Okay, so the question says, given the function defined piecewise as x plus 3 over x squared plus 7x plus 12 on the interval from negative infinity to negative 3, polynomial x squared plus 3 defined on negative 3 on the interval from negative 3 to 2, negative 3 included, and the rational function x plus 9 over x plus 3 on the interval from negative 2 to infinity. The question is, identify the points of discontinuity and classify them. That means say whether we're talking about infinite discontinuity, removable discontinuity, or jump discontinuity, and B, write the equations of all the horizontal and vertical asymptotes, if any. Okay, so two questions. What I suggest you to do is to observe this function on the interval from negative infinity on the real line, right? And then split it up the way it is defined here, the way it is defined, the way the function is defined. So from negative infinity to negative 3, so to negative 3 right here, this is the first function, the first part of the function that we're going to analyze. Then from negative 3 to negative 2, sorry, this is negative 2, my bad. Okay, so it's defined at negative 3, okay, all the way to negative 2, and then from negative 2 all the way to positive infinity. So I have three intervals from negative infinity to negative 3, from negative 3 to negative 2, and from negative 2 to infinity. And then of course I have to check what happens at x is equal to negative 3 and what happens at x is equal to negative 2. But right away I can see that the function is not defined at negative 2, which means that f of negative 2 does not exist. So right away we can expect that when we're going to get to there, because I'm going to analyze interval, then x is equal to negative 3, then this interval, and then when I'm going to get to x to negative 2, right away I will know that the function is going to be discontinuous. Why? Because the function is not defined. Simply negative 2 is not part of the domain, so f of 2 does not exist. Okay, but we'll get to there. So answer, first of all, we have on the interval from negative infinity to negative 3, on this interval the function f of x is defined as x plus 3, x squared plus 7x plus 12. So this is a rational function. We have a polynomial over polynomial. This function will not be defined for the values of x where the denominator will be 0. So why don't we find those values? You can easily see that the denominator can be factored as x plus 3 times x plus 4, right? And from here, the denominator is 0, which means the function is not defined for the values x is equal to negative 4 and x is equal to negative 3. But now be careful, x is equal to negative 4 indeed belongs to this interval, but x is equal to negative 3 doesn't belong. Why? Because it's not included in this interval. So we're not going to talk about this point yet, okay? We're not going to talk about the point x is equal to negative 3 yet. So definitely, since f of negative 4 does not exist, we can say that f of x is discontinuous at x is equal to negative 4. Okay. Now, if we want to talk about the type of discontinuity, we have to address, we have to use limits. Okay. So what happens limit of f of x when x approaches to negative 4? And now you can choose a side here, left or right. Let's say left. Then the limit of when x approaches to negative 4, right? Definitely negative 4 is less than negative 3 is in this interval, which means f of x is this, okay? X plus 3 over this denominator that was already factored, right? So that's x plus 3 times x plus 4 as x approaches to negative 4 from the left. Cancel the common factor, and we are left with the limit of 1 over x plus 4 as x approaches to negative 4 from the left. While the numerator stays at 1, the denominator approaches to 0, that ratio will blow up to infinity. Now you just have to determine whether it's going to be positive or negative infinity, depending on the side that you decide to approach to, okay? So we said let x approach to negative 4 from the left when I have numbers that are smaller than negative 4, right? So let's say negative 4.1 or 0.001 plus 4, that will give you a negative number, so this approaches to 0. But from the left, so it's negative, right? Positive divided by negative gives me a negative infinity. So what do I know? What does this tell me right away? It tells me that I'm talking about infinite discontinuity at x is equal to negative 4. But if I talk about infinite discontinuity, that means what? That x is equal to negative 4 is nothing else but the equation of the vertical asymptote. So I will take a note of that so that I can answer the second question later on. So x is equal to negative 4, we have infinite discontinuity at x is equal to negative 4. Okay. Now we move on to, so we are done with this interval right here. Okay, we know that rational functions are continuous on their domain, and on this interval right here, the function was not defined, only at negative 4. So we are done with this interval. We move on to the point x is equal to negative 3. At x is equal to negative 3, first of all, let us see whether this function is defined, whether I can evaluate f of negative 3. Okay, when x is equal to negative 3, f of x is this value right here. So that's negative 3 squared, sorry, f of x, not this value, f of x is defined as x squared plus 3. So f of negative 3 is negative 3 squared plus 3, and that's equal to 12. Okay, in order to prove continuity at negative 3, what needs to be satisfied? We need to show that the limit as x goes to negative 3 of f of x is equal to f of negative 3, which we evaluated that it is 12. But now this limit here exists when both one-sided limits are equal. Okay, so in order this limit to exist, I need the limit as x approaches to negative 3 from the left of f of x to be equal to the limit as x approaches to negative 3 from the right of f of x. So this is the limit as x approaches to negative 3 from the left. When I'm approaching negative 3 from the left, okay, that means that the values are less than negative 3, so f of x takes on this definition. So that's x plus 3 over, I've already factored this denominator, x plus 3 times x plus 4. You cancel these two, cancel these two values, use direct substitution, and you get 1 over 1, which is equal to 1. Okay, when x approaches to negative 3 from the right, that means x is greater than negative 3, so f of x becomes x squared plus 3, so that's limit as x approaches to negative 3 from the right of x squared plus 3, which is equal to 12. And since these two limits, and since these two limits are not the same, this implies that the limit of f of x as x approaches to negative 3 does not exist. Okay? And if the limit does not exist, then this equation right here cannot be satisfied. Okay? So that means that we have discontinuity at x is equal to negative 3. Okay, now let us determine the type of discontinuity. Okay, since limit of f of x as x approaches to negative 3 from the left, this limit exists, that is equal to 12. In other words, it's not neither positive nor negative infinity, but is not equal to the limit as x approaches to negative 3 from the right. That was equal to, sorry, this one is just 1, from the left is just 1, is equal to 12, we can conclude that we have a jump discontinuity. So at x is equal to negative 3, we have jump discontinuity. Why? Because both one-sided limits are not equal, right? They are some constants. They're not neither positive or negative infinity, so we don't talk about infinite discontinuity, but because they're not equal, we have jump discontinuity. Okay? So we're done with the point x is equal to negative 3. Now we discuss what happens on the interval from negative 3 to negative 2. Okay? On the interval from negative 3 to negative 2, okay? When x is between negative 3 and negative 2, f of x is x squared plus 3. F of x is equal to x squared plus 3. And as a polynomial, this polynomial is continuous on R, on any interval, on the interval from negative infinity to positive infinity, so that means it's definitely continuous on this interval. F of x is equal to x squared plus 3 is continuous for all the values of x in the interval from negative 3 to negative 2, because as a polynomial it is continuous on R. Okay, so that was very easy. So we're done with this interval also. The function was defined as a polynomial in this interval, so it's continuous. Now we are at negative 2. And as I can see, the function is not defined when x is equal to negative 2. Basically, f of negative 2 does not exist. So right away, we can see that we're talking about discontinuity. When x is equal to negative 2, f of negative 2 is not defined, or it does not exist, right? Which means f of x is discontinuous. At x is equal to negative 2. Now, the bigger problem, the bigger question is what type of discontinuity it is. Okay? So again, in order to answer that, we need to look at the limits, right? So the limit as x approaches to negative 2 from the left of f of x is equal to the limit. This means for all the values less than negative 2, when x is less than negative 2, this is the definition of the function, x squared plus 3. So that's x squared plus 3. By direct substitution, that's 4 plus 3 is equal to 7. On the other hand, limit of f of x when x approaches to negative 2 from the right is equal to the limit as x approaches to negative 2 from the right, when x is greater than negative 2, the definition of the function is x plus 9 over x plus 3. And by direct substitution, negative 2 plus 9 over negative 2 plus 3 is equal to 7 over 1, which is equal to 7, sorry, which is equal to 7. Okay, so what do we have now? Now we have a situation where the limit of f of x as x approaches to negative 2, indeed it exists because the one-sided limits here are the same. Okay, it's equal to 7, but is not equal to f of negative 2 because f of negative 2 does not exist. And hence we talk about removable discontinuity. Removable discontinuity at x is equal to negative 2. Okay, so the situation is something like this. So at negative 2, function goes like this, and this is 7, right? The function is not defined at negative 2. And finally, we have to discuss about the function on the interval from negative 2 to positive infinity. When x is greater than negative 2, f of x is defined as the rational function x plus 9 over x plus 3. So on the interval from negative 2 to positive infinity, f of x is equal to x plus 9 over x plus 3, and this is a rational function, continuous everywhere but at negative 3. But negative 3 is not part of this interval, right? Which implies that f of x is continuous on this interval. Okay, so the points of discontinuity were what? X is equal to negative 4, where we have infinite discontinuity. We have jump discontinuity at x is equal to negative 3, and we have removable discontinuity at x is equal to negative 2. Now to answer part B, when do we have vertical and horizontal asymptotes? Remember that vertical asymptotes happen when either one of the 6 limits, and I will write these 6 limits as x approaching to a, either from the left or from the right, or at a itself, is either positive or negative infinity. So from our analysis of this function, on the whole interval from negative infinity to positive infinity, we saw that there is only one point such that when we approach to that point from the left or from the right, the function blows up to positive or negative infinity, and that's the point x is equal to negative 4. So basically we have vertical asymptotes at the point where we have infinite discontinuity, so we have vertical asymptote. The equation of the vertical asymptote is x is equal to negative 4. Now in order to answer the horizontal asymptotes, we have to check the behavior of the function at negative infinity and the behavior of the function at positive infinity. Okay, and if these two limits end up being some constants, be careful, constants, real numbers, then we can conclude that y is equal to L1 or y is equal to L2, depending if these two are actually going to end up being constants, are the horizontal asymptotes. If the limit blows up to positive or negative infinity in either of these two, then we don't have horizontal asymptotes. Okay, so let us evaluate these two limits. With that, we're going to finish this question. So limit of f of x as x approaches to negative infinity is equal to the limit negative infinity, sorry. As we're going towards negative infinity, that means we are talking about definitely numbers less than negative 3. When x is less than negative 3, f of x takes on this definition. So that's x plus 3 over x squared plus 7x plus 12. Okay. As x goes to negative infinity, the numerator goes to negative infinity, the denominator goes to positive infinity. Okay, so I have infinity over infinity situation that I solve by factoring out the highest exponent, x, 1 plus 3 over x squared, 1 plus 7 over x plus 12 over x squared. Okay, where I cancel the factor of x, and then I send x to negative infinity. A constant divided by something that goes to positive or negative infinity approaches to 0. Okay, and then this simplifies to the limit of 1 over x as x goes to negative infinity, and this limit is 0. If I have a finite constant divided by something that goes to negative infinity, the ratio will approach to 0. Since the limit of f of x as x goes to negative infinity is equal to 0, the first horizontal asymptote is y is equal to 0. And now we repeat the same procedure for the limit of f of x when x goes to infinity. That means that we are talking about positive values, and for all the values greater than negative 2, the function f of x is defined as x plus 9 over x plus 3. As x goes to positive infinity, both the numerator and the denominator approach to infinity. We proceed solving this limit by factoring out the highest exponent, cancel the x's, send x to infinity, in which case both of these terms go to 0, so 1 over 1 is equal to 1. So the other horizontal asymptote is y is equal to 1. And the second question that we're going to do about continuity is this one here. Again, you can pause the video right now, copy the problem, and try to solve it by yourself first. Find the values, only one value or many values of C such that f defined as this is continuous on R. Okay, so the way we define f is 9 minus x squared over x minus 3 if x is less than 3. And c squared, where c is a constant, minus x for all the values when x is greater than 3, okay? Okay, so for all the values less than 3, okay, f of x is defined as 9 minus x squared over absolute value of x minus 3. And this is continuous. Why? Because it is defined. This function will not be defined only at 3, right? It's continuous. Because this rational function here will be continuous whenever, wherever it is defined. It will be continuous on its domain, and definitely its domain on this interval, right? Be careful, I'm excluding the point positive 3, my bad, sorry. I'm excluding the point 3. And then for all the values greater than 3 on the interval from 3 to infinity, f of x is a polynomial, is a linear function since it is a linear function. So the only question that the only question that is left is what's happening at 3. Okay? So we have to make sure that we find the appropriate value of c for which the function will be continuous at 3. In order the function to be continuous at 3, this condition has to be satisfied. F of x, as x approaches to 3, has to be equal to f of 3. Okay, let's first check how much is f of 3. When x is equal to 3, this is the definition of f of x, so that's c squared minus 3. Okay. On the other hand, this limit here will exist when both one-sided limits as x approaches to 3 are the same. So when I'm approaching 3 from the left, x is less than 3, so f of x takes on this definition, 9 minus x squared over x minus 3, as x approaches to 3 from the left. And this is an absolute value. Use direct substitution right away, and I get 0 over 0, right? How are we going to solve that limit? Well, the numerator can be factored, but now the denominator, we have to talk about the denominator, we have to get rid of the absolute value. Okay, and whenever we're dealing with the absolute value, x minus 3 in absolute value can be either negative x minus 3 if x minus 3 is less than 0, or positive x minus 3 if x minus 3 is greater or equal to 0. So let us determine. If x approaches to 3 from the left, okay, for all of these values that are on the left of 3, all of these values are less than 3. So that means that x minus 3 will be negative. A smaller number than 3 minus 3 is less than 0, which means that absolute value of x minus 3 will be negative x minus 3. So absolute value of x minus 3 becomes negative x minus 3. But negative x minus 3 is nothing else but 3 minus x. And now when we try direct substitution, we get 3 plus 3 is equal to 6. Okay? And then the limit as x approaches to 3 from the right of f of x is equal to the limit as x approaches to 3 from the right. That means I'm talking about x's that are greater than 3, and I look at the definition of the function. For all the x's greater than 3, f of x is c squared minus x. Use direct substitution and you get c squared minus 3. So in order this limit here to exist, these two one-sided limits have to be the same. C squared minus 3 has to be equal to 6. Now, in order not to make mistakes, you should here solve this quadratic equation by bringing all the terms on one side and then factoring. So c squared minus 3 minus 6 is equal to 0, c squared minus 9 is equal to 0. From here, we factor this as c minus 3 times c plus 3 is equal to 0, from where I have c is equal to 3 and c is equal to negative 3. So for these two values of c, the function here is continuous on R, because we said that it's continuous for all the values less than 3. For all the values greater than 3 is continuous. The only questionable point was what happens when x is equal to 3. And then here we concluded that the function will be continuous at 3 if either c is 3 or negative 3.